All right, here is the last block of 12 for the AP Chem exam. I actually don't think that this is too bad in here. Okay, so question 48 through 52 refer to the following. The pH of solutions of 4 acids prepared at various concentrations were measured and recorded in the table above. The 4 acids are in no particular order, blah, 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 blah. Who cares about that? For which acid is the value of the acid dissociation constant Ka the smallest? So what you need to understand to do this problem is when Ka is the smallest, that means it's the weakest acid. Remember, weak acids don't dissociate very much, so if it has a small dissociation constant, it's not dissociating. Now, the other thing you got to keep in mind that for acids, the highest pH is the weakest acid, because the way we define pH in chemistry is pH of 7 is water, and it's the distance from 7. So acids have low pHs. Strong acids have low pHs, and strong bases have high pHs. And then weak acids and weak bases are closer to 7. So it's really weird. Low pHs are very acidic. High pHs are very basic. And so it's opposite. The lower the pH, the stronger the acid. So basically this question is saying, and just pick a concentration. At this concentration, acid 1 has the absolute highest pH. It's the closest to 7. That means acid 1 is the weakest acid. It's not a bad problem. This one, which one is hydrochloric acid? So this is what you got to know. Hydrochloric acid is a strong acid. It dissociates completely. I would pick probably this because it's very easy to take the pH of this. So if we do an ICF chart, and this starts out 0.010 molar, and then there is no X. There is no X. We know that strong acids dissociate completely. It's no variable. We know what it is. And so this is going to go away, and this is going to drop to 0. And this is a 1-to-1-to-1 mole ratio. So this is going to be a 1-to-1 mole ratio. So this is 0,100, and this is 0,100. And pH, so the pH is the negative log of 0.010. Think of this as 1 times 10 to the negative 2. So the log base 10 of 10 to the negative 2 is negative 2. Moral of the story, the one that has a pH of 2 is hydrochloric acid. The one that has a pH of 2 is acid 2. The other way you can do that problem is that is absolutely the lowest pH, and so that lowest pH is the strongest acid. So there's a lot of different ways to do that one. Which of the following has the greatest concentration in a 1 molar solution of acid 1 at equilibrium? So what you got to know from 2 questions before is that acid 1, which I'm going to call HA, is a weak acid, which means when you throw it into water, it turns into H3O+, because using Bronsted theory, acids donate their protons, and A-. Now, the deal is weak acids don't ionize very much. It's less than 90, it's less than like 3 or 4%. So you could make the argument that at the end, you have 97% of this is still together and 3% of it has dissociated. It's very small. And so because it is the absolute, HA is the absolute weakest acid because it has the highest pH. Remember, distance from 7. And so the thing that has the greatest concentration is the acid. It's not the conjugate base of the acid. That would be this. We only have 3%. It's not this. And it sure as heck isn't this, because when you have an acidic solution, you have more acid than, you have more H plus than OH minus. So the only answer that makes sense is C. All right, 52. This is this is the trick question again. You have 4 acids. They all have a concentration of 0.5. They said that. They all have the same volume. It says equal volumes and are titrated with the same strong base. Which will require the greatest volume of base to reach the equivalence point? And the answer is B. They all take the same volume, because here's the equation. MA times VA equals MB times VB. This only works on the AP exam because you got to have a 1-to-1-to-1 ratio. Volume of the base then is the molarity of the acid. They're all 0.5. Volume of the acid, I don't know what it is, but it says it's equal volumes of the 4 acid, and you're titrating them with the same base. So for all 4 of them, this is the same, this is the same, this is the same. Equivalence point doesn't have anything to do with acid or bases. Sorry, strong acids or strong bases. It just has to do with when do you add the same amount. Equivalence point is when you have an equivalent amount of acid and an equivalent amount of moles of acid and an equivalent amount of moles of bases. This one is probably the toughest. Here's what I need you to see. 25, 25. The volumes are the same. The acid is 0.1 molar. The base is 0.5 molar. So what you can see if you understand that equation is you are at the half equivalence point, because MABA equals MBVB. And so let's just say the molarity of the base. Well, I guess that's not really the way to do it. Anyways, just so that you understand, these aren't equal. These aren't equal because the volumes are equal, but this is half of this. So you're actually at the half equivalence point. And, okay, you're not equal because this is what you use to find the equivalence point. Well, if this is 25 mils and this is 25 mils, and this is 1 molar, and this is 0.5 molar, you can see that they're not equal, but one is exactly half of the other. Now, why that's important in this problem is HA is a weak acid, and NaOH is a strong base, and when these interact, you get NaA plus H2O, and so this is a weak acid, this is a strong base, this is a salt, this is water. However, this is actually the salt of a weak acid. In other words, they have a common ion. And because you are at the half equivalence point, we have a buffer system because you have a weak acid and the salt of the weak acid. And you have an interesting thing with the buffer system. So the pH is equal to the pKa plus the log of the conjugate base over the acid. Because we're at the half equivalence point, this is 1, and the log of 1 is 0. And so, anyways, what this says is, I gotta hit this, hang on. All right, we are re-recording. Okay, so what you need to know is we have a buffer system. So the question is, which of the following best explains what happens to the pH of the mixture when you add a few drops of HNO3? So what happens is, and by the way, this is important. I need to do the net ionic equation to explain part of the answer. So this dissociates into Na plus OH minus, and then this dissociates into Na plus A minus, and this we leave alone. And so the net ionic equation says you have a weak acid and a strong base, and you make, this is actually the conjugate base of a weak acid and then water. And so first thing, if you put it, what happens when you put a few drops of NaOH, and the first thing, or sorry, HNO3 is strong acid, you need to know that the pH is not going to change much, because the definition of a buffer system is that it can resist changes in pH when you just add a little bit of acid or base. Now, both of these answers make sense. The pH stays about the same because that's what a buffer does. Now, why does it stay the same? And the thing about titration is these don't go to equilibrium, they go to completion. Well, what happens is if you put some H plus in there, now remember you have this because you we're at the half equivalence point. So we have this still in the beaker. This isn't in the beaker because we're at the half equivalence point. All of the base is gone. And so what we have in the beaker is this, and water doesn't do much. And why does the pH not change? Because if you put H plus in there, it reacts with the A minus, making HA, and the pH doesn't go up because pH measures H plus. Well, if you put a few drops of H plus in there, it's going to hook up with the A minus, and you're going to end up with HA. You can think of it as equilibrium though too. But this makes the most sense. So the reason is the pH stays about the same because the conjugate base of acid 1, which is A minus. Remember now, if HA is a weak acid, then A minus is a strong conjugate base. The strong conjugate base hooks up with the strong acid, and they neutralize each other, and the pH doesn't change much. Okay, 52. No, that was 52. Oh, a proposed mechanism, let me move this down, for the destruction of ozone gas in the stratosphere is represented above. Which of the following is evidence for the fact that the mechanism is occurring? Now, I want to get the overall reaction by adding these. So this cancels this. And I think we end up with Cl gas plus CO3 gas plus O gas goes to Cl plus 2O2, just to check to see if it's balanced. 1 chlorine, 3 and 4 oxygen, 4 oxygen. Okay, so now, which is the following is evidence for the mechanism that this is occurring? Now, if you add chlorine, ooh, interesting. Oh, these also cancel. These also cancel. I'm an idiot. This is then a catalyst because it's there in the beginning, and this is an intermediate. And so we end up with is O3 gas plus O gas goes to 2O2 gas, which is balanced. Okay. The presence of CLG gas increases the rate of the overall reaction. That is absolutely true. Why? Because Cl is a catalyst. What do catalysts do? They increase the rate of the reaction by lowering the activation energy. B is wrong because the presence of Cl doesn't decrease the rate of the reaction. The reason why you add a catalyst is because it makes the reaction go faster by lowering the activation energy. And then this equation has nothing to do with equilibrium. It doesn't have any double arrows. The only answer that makes sense is A. Okay, here we go. And this is about ionic bonding. Now this is crazy. This is probably the hardest one in this section. Okay, so here's the deal. We have two compounds. These are ionic compounds, and ionic compounds are governed by Coulomb's law, which is a force is of attraction between charged particles, and ions are charged particles, is a function of the magnitude of the positive charge, meaning absolute value, times the magnitude of the negative charge, over d squared. Okay, so first thing, this is almost twice as big as this. Why does MgO have such, the boiling point is much, much, much larger? Well, it doesn't have much to do with size, because if you look, sodium and magnesium are roughly the same size. They're only 4 picometers apart. And fluorine and oxygen, which are right next to each other on the side, they're not much different. Sorry, fluorine and oxygen, not chlorine and oxygen. So fluorine and oxygen aren't much different. They're only 7 picometers apart. So this is telling you that this huge distance between the boiling point of NAF and the boiling point of MgO is not attributable much to size. What's causing this is sodium has a +1 charge and fluoride has a -1 charge. So the force of attraction from sodium fluoride is 1, the absolute value of 1 times the absolute value of -1, which is 1. Okay. And then when you do MgO, it's +2 and -2. And so this is like 4K over D squared. This is 1K over D squared. So what I need you to understand is, first of all, the huge difference in these boiling points is a function of the charges of the particle, not a function of size. That's the first thing you want to know. Now, erasing all of this, okay, this question is about, based on the data in the table above, which of the following statements provide the best prediction for the boiling point of NaCl? And the first thing you need to understand is that NaCl is a lot like NaF. That's why they gave you the top table, because this is +1 -1, and this is +1 -1. These have the same charges. So the difference in boiling point between sodium chloride and sodium fluoride must not be a function of their charges, because they're the same. It must be a function of the distance. And so what you'll notice is, obviously this and this has the same size on the chart. This is 181 picometers. This is 133 picometers. This is 76 picometers, and this is 76 picometers. And so ionic radii is the distance between the nuclei. And so this is 76 plus 181, where this is 76, obviously not drawn to scale. This is 133. So what you need to know is that there is a bigger distance between sodium and chlorine than there is between sodium and fluorine, according to the chart. Now, the force of attraction is this. This is what you got to know. As the distance goes up, obviously D squared goes up. And then, but the force of attraction is K times the magnitude of the positive charge times the magnitude of the negative charge over D squared. Well, when you divide by a bigger number, the force is weaker. And if you have a weaker force, you have a lower boiling point. So keep in mind, sodium chloride has a greater distance. The distance is squared, which makes it even bigger. When you divide by a bigger number, the force gets weaker or smaller, and the boiling point goes down. So let's think of what our choices are. NaCl has a lower boiling point than NaF. That's true, because the Coulombic attractions, this is Coulomb's law. A is the answer, I think, but let's look. NaCl will have a boiling point between Na and F and MgO. Nope. The boiling point is going to be lower. It's not going to be between them. It's going to be over here. NaCl will have a higher boiling point than MgO. Nope. +1 -1, +2 -2. No way. And NaCl will have a higher boiling point than MgO because, and then they just make up stuff that sounds good. NaCl has a lower boiling point than NaF because the Coulombic attraction. Remember, Coulomb's law is what you need when you have charges. Ionic compounds have charges. Okay, there you go. Coulomb's law keeps coming up over and over and over again. All right, next one. I love this. Table 55 above shows the values of Ka for 4 weak acids. Which of the following pairs of chemical species combined in equal molar amounts? Very important, equal molar amounts. That means that the ratio is, okay, so first of all, buffer. What do buffers? First of all, buffer is made out of a weak acid and the salt of a weak acid. Nope, weak acid, but this would have to be NO2 minus to be a buffer. Okay, weak acid, conjugate base of the weak acid, this would work. Weak acid, conjugate base of a weak acid, this would work. Weak acid, conjugate base of a weak acid. Now, here's Henderson-Hasselbalch. The pH is equal to the pKa plus the log of the conjugate base over the acid. So this is the acid, this is the conjugate base, or this is the acid. And because they said equimolar, these are equal, so this is 1. So this is a very easy problem. Not when you took the test, but after I did. You want the pH closest to 7.5. So here you go, my people. All right, hang on. Come on, move for me. Oh, over here. Here we go. You ready? This is crazy. Where did my chart go? Mrs. Hyde's walking across the room. You can't see it. Where did this chart go? Let me drag it down here. I don't know. So I'm going to write this in a different color because I ended up moving this stuff when I was moving. Okay, this pH would be between 3 and 4. This pH would be between 5 and 4. This pH would be between 7 and 8. And this pH, that's a negative 10. You can't really see it. That pH would be between 10 and 9. Which one would be the best choice if you want the buffer to be 7.5? The answer is the one that has HClO in it. So it's C. I'm thinking if we would have done this test after this, okay, in my opinion, this is one of the toughest ones on the whole test. And here's the deal. Beaker X and beaker Y each contain 1 liter of solution shown above. So you have 1 liter of this and 1 liter of this. And then obviously when you put them together, you're going to get 2 liters. A student combines the solutions by pouring them into a larger previously empty beaker D and observes the following formation of a white precipitate. Assuming that the volumes are additive, which of the following sets of solutions could be represented by the diagram? Now, here's what you got to know, guys. If you take 2 solutions and mix them together, the concentration of each solution is going to go down because you just doubled it. So the first thing you got to know is when you take 2 solutions, I don't care what the concentrations are. The concentration of both of them is going to go down. So first of all, because concentration is moles per liter, and so if you're thinking of them separately, this can't be 2 molar and this can't be 2 molar and this can't be 4 molar because it has to be less than 2 molar. This can't be 2 molar and this can't be 2 molar and this can't be 2 molar. First of all, A goes up, B. Now, C could work because maybe, I don't think so. But here's the deal. What I need to do now, this is the one thing I figured out when I was taking the test myself. I need to write the equation because mole ratios are important. AgNO3 is in the first beaker. MgCl2 is in the second beaker. And when you combine them, you're going to get silver chloride. Chlorides are soluble as lead, except for silver, mercury, or lead. So that's why the silver chloride is sitting on the bottom. Plus magnesium nitrate. But because of this magnesium nitrate, because there's a 2 here and a 2 here, I need to put a 2 here, right here, and right here. And the first thing you're going to see is that we have a 2-to-1 mole ratio. So right now, these are both pretty good. This is a 2-to-1 mole ratio. This is a 2-to-1 mole ratio. This is a 2-to-1 mole ratio. Now, the question is it 2 molar and 1 molar? I don't think so because it has to be less than both of them. But this is what I want to show you when I do D. I'm going to extend this. I'm going to do this. Anytime you mix 2 solutions, we do a ICF-VM chart. But this is mole, and this is mole, and this is mole, and this is milliliters, and this is molarity, which is moles per liter. Okay, so let me just convince you that D is right. The reason why I'm throwing out C is the concentration can't stay the same because when you double the volume, the concentration should change. Okay, so here's the deal. 2 moles per liter times 1 liter is 2 moles. So AgNO3 is 2 moles. And then MgCl2, now I'm doing D, is 1 mole. because 1 mole per liter times 1 mole. And then this is MgNO3 is 0. And AgCl we don't even think about because solids don't have concentrations. Okay, now this is a 2 to 1 mole ratio. So apparently these are going to run out at the same time because the way the mole ratio is that you need to have twice as much of this as this, and we do. And so these are going to run out at the same time. This is -2, this is -1. This is a 1 to 1 mole ratio. So either you put +1, or if you think about it this way, this is 2 moles, but this is a 2 and this is a 1. So this number has to be half of this number. And so then the change is 2 minus 2 is 0. 1 minus 1 is 0. 0 plus 1 is 1. And then what is the new volume? Well, 1 liter plus 1 liter is 2 liters. Okay, I'm going to change this to liters. This is 2 liters. This is 2 liters. 0 over 2 is 0. 0 over 2 is 0. 1 over 2 is 0.5. This is the best choice. And without doing this whole chart, know that if you mix 2 solutions together, the new concentration has to be smaller for both of them. Obviously, 0.5 is, sorry, up here. 1 is smaller than 2, but 1 is not smaller than 1. So best choice is D. 57 is one of my favorite problems because they want to know is this 0 order, first order, or second order? And so here are the things that, and you will have a formula sheet. 0 order is when you graph time versus the pressure, just the pressure, nothing funny, it will be linear if it's 0 order. If you graph time versus the natural log of the pressure, it will be linear if it's first order. And if you graph time versus the reciprocal of the pressure, it will be, and that's linear, it will be second order. So this is second order, this is first order, this is 0th order, they call it. Okay, now, how do you do this without a calculator? Well, you have to understand the concept of slope. That slope has a constant rise over run. So look at here. Let's do the x-axis. This is 100. This is 100. This is 100. Is that constant? This is 75. This is not 75. I think it's 75 minus 38. 15 minus 8 is 7. Okay, so 75 minus 38. I got it right nicer. 6, 1, 7. This is 37. And then 38 minus 19 is like 19. You can see this is not constant. It's not 0 order. 0.7, 0.7, 0.7. Rise, run, rise, run, rise, run. It's looking like it's first order. If you subtract these, and I don't even know if you need to subtract them. I don't know. Can you see that they're not, it's not linear? If I do the top one minus the bottom one, 0.0130, I'm going to put the 0 in, so it's minus 0.0067. This is going to be 3 and then 6. So then this is negative 0.0063. And then this is negative 0.014. You can see that we're not getting 0.006, 0.014 negative. It just makes sense to me because this has the same rise and the same run that it has to be first order. Without a calculator, you can't haul out those fancy equations. Okay, wrong way. Okay, this one, I love this problem because this was chapter 8. So let me just do the periodic table. Okay, I just want you to see this. This is potassium. This is calcium, both in the fourth period. We learned that the radius decreases left to right. It doesn't have anything to do with shells and shielding electrons because potassium and calcium both have 4 shells and they both have 18 shielding electrons. But what's going on is potassium is in row 1A, so it has an effective nuclear charge of 1. Remember, effective nuclear charge is what you get after you take the valence electron, or sorry, the total electrons and subtract the shielding electrons. Calcium is 2A, so it has an effective nuclear charge of 2 electrons. Sorry, an effective nuclear charge of 2 in the nucleus pulls the electrons in tighter than when you have an effective nuclear charge of 1. Doesn't pull in as tight. So first thing, the radius decreases left to right because of greater ZEF. And so the first thing is, when we're doing potassium, we know that calcium is smaller than potassium. So this number has to be larger than 194. Now remember, this is the opposite trend. Anytime the radius decreases, the ionization energy increases. Why? Because if the force is stronger, it holds the electron tighter and you need more energy to get it to move. And so calcium, and again, this is because of greater ZEF. Calcium needs to have a bigger ionization energy than potassium. More energy means more difficult to get the electron. So this one needs to be less than 590. What is the only choice that the first one is bigger than 194 and the second one is less than 590? The only thing that matters is, or works, is B. 59, okay, here's the thing I got to tell you about this question. This bond is not dotted, it's inside the HF molecule. That is the covalent bond. Bonding is how you, inside the molecule, how do the atoms connect to each other? And this is referred to, nobody uses this term, intramolecular force. That's a force inside the atom. Now, this dotted line is an intermolecular force. It's called a dipole-dipole force. And there's a very special kind of intermolecular force, dipole-dipole force that's very strong. It's called the hydrogen bond. So what happens on HF, the electrons shift this way, this side takes on a partial negative charge, this side takes on a partial positive charge, and then the next HF molecule orients itself this way because the positive side of this molecule is attracted to the negative side of this molecule. Anyways, what you need to know on this diagram, the solid line is shorter because bonding inside a molecule is more difficult to break than intermolecular forces. So notice, this is 100 picometers. These are closer and tighter together because this is a stronger force, and this is 150 picometers. And what accounts for the two different distances is the difference in strength between covalent bonds and intermolecular attractions. That's the only thing that makes sense. And then finally, oh, I love this problem. Watch me. If the math is easy without a calculator. So COCl2, there's your equilibrium system, which means you got to set up an ice chart. And then, so I do I, C, E, but now this is P pressure, so these are atmospheres. And if you read the problem, it says the pressure in the flask is initially 1 atmosphere. And then this is going to go down X, and this is going to go up X, and then 0, this is X, and this is X, and this is 1.0 minus X. And then if you go over here, Kp is the pressure of the CO times the pressure of the Cl2 over the pressure of the COCl2. But here's the crazy thing. After it reaches equilibrium, which means you're in the E row, the total pressure is 1.2 atmospheres. And remember, Dalton's law of partial pressure says the sum of the pressure, the total pressure is the sum of the individual pressures. Now, without a calculator, this is pretty easy. X plus 1.0 minus X equals 1.2. This plus X minus X, so we end up with X plus 1.0 equals 1.2. And X, when you subtract 0.1 from both sides, is 0.2. So this is 0.2. And this is 0.2, and this is 1.0 minus 0.2. This is 0.8, and just check, it's 0.8 plus 0.2 plus 0.2, 1.2. These need to have a 1-to-1 mole ratio because they're on the same side. These went up 0.2, so this needs to go down 0.2, so everything's groovy. Now, that's not the question. The question is, what's the equilibrium constant? Well, it is going to be 0.2 times 0.2 over 0.8. Okay? Last time I checked, 2 times 2 is 4. This is 0.04. This is 0.8. Old-fashioned division, 0.8 goes into 0.04. If you remember this from grade school, whenever you have a decimal, you make this 10 times bigger and you make this 10 times bigger. Does 8 go into 0? No. Does 8 go into 4? No. 8 times 4, sorry, 8 times 0 is 0. 4 minus 0 is 4. Bring down the 0. Does 8 go into 40? You bet 5 times. This is the only solution that matters. Or you can look right here and see, you know, this 4 and this 8. This is 0.5. I mean, it's a half. And then the only one that has a 5 in there. However you want to do that, that's a very good problem. And that is the last 12 problems. And I did not think that those were that bad.